We have an RLC circuit. Without the driving voltage. Or if we have it with the driving voltage, we can write the equation, whatever the driving voltage function is over here. We solve the homogeneous equation, and then we add that to any particular solution. Now, everybody I'm talking to right now has had differential equations, so I think you know what I'm talking. If you haven't had differential equations, well, we're going to solve this equation here. Okay? And it's pretty easy to solve if you just let Q equal E to the RT. Plug that in, Q double prime will be R squared E to the RT, Q prime will be R E to the RT, so forth. Your E to the RTs divide out of the equation, and you end up with a characteristic equation. Now, we've done some of those steps earlier, so I'm just kind of summarizing. We solve the characteristic equation. We just use a quadratic formula, just using it literally. We get this. Okay. So that Q equals Q naught E to the RT, or R, little r. Little r is characteristic. We've got a big R2, that's your resistance. Anyhow, this should be some Q naught E to the RT, where R is, well, is this. I've got the plus or minus. That obviously gives you two equations, but that's okay, or two, but we'll worry about that in a minute. Okay. Now, E raised to this power plus this power is E raised to this power times E raised to this power. It's just your basic rule of exponents that some people go a little blind on when they see this, but I'm sure you understand that. So here's our general, here's our solution to the what we call the homogeneous equation. Okay, to this equation. Now, if this thing is greater than or equal to 0, this gives us a decreasing function of t, because you have a negative in front of the t. Your exponent, it's presumably, we understand exponential functions pretty well by this point. Note that if we keep it in this form without breaking it into two parts, in other words, without breaking this down to e to this power and e to this power, the magnitude of quantity R over L squared minus 4 over LC is less than the magnitude that you would get if you didn't have the minus 4 over LC. And square root of that, if you didn't have the 4 over LC here, would be just R over L. So we have negative R over L plus or minus something that is at most equal to R over L. Okay, so it follows that the exponent here is negative in all cases, or possibly 0. But that's if you don't have an L or a C in there. Okay. So that's why I make this comment. We're not going to talk about these solutions. You take more advanced courses or later courses that aren't all that much more advanced and deal with that. And you've dealt with this sort of thing in differential equations. I'm not assuming everybody that might be listening to this has had differential equations, but I explained how this comes about, okay? It then turns out if this discriminant here, this expression under the radical is negative, then we could write this e to the plus or minus square root of r squared minus 4 over LC times t as, well, we can write this expression as the negative of this expression times -1. Or -1 times this expression. We take -1 times this expression and we get this expression. 4 over LC becomes positive. The R over L quantity squared becomes negative. and then it's times -1. Well, that would then give us the square root of this times the square root of -1, so we get an I here. So we get this, and then knowing Euler's identity, we can write this as cosine of omega t plus I sine of omega t, where omega equals this thing, okay? And that's all straightforward mathematics. Most of it not even at the level of differential equation, most of it at the level of calculus 2 in the Euler identity, which everybody's had calculus 2 should be familiar with. Okay, Euler identity says comes about if you just know what the Taylor expansions are of the sine, the cosine, and the exponential function. It's an immediate consequence. Just write it out, and it's really kind of easy. Okay. Now getting from this to this, just you have arbitrary coefficients in these things, and you can rearrange this in such a way that you have this form. And that's done in differential equations. I don't want to do that much trigonometry. I don't want to take the time to do it. It's kind of neat. So it's not difficult. But we're not going to do that. End up with this function. Then real reason I give you this function is we're going to attempt to see what happens adjust our L and C, our RL and C. Actually, if we adjust our driving voltage, match the natural frequency, which is what this omega is. Okay. I'll point out also, if R was absent, then we wouldn't have this exponentially decreasing term. Okay. In that case, we would just have simple oscillating result. Take this term out, we just have a sine function, basically, sine with a certain phase. Okay. So we've got a function generator that more or less works, but it kind of gives us a square wave. We do the same sort of thing with a square wave. It isn't quite as nice. And we can't seem to get it to give us a sine wave, but we can turn the dial, change the frequency to match eventually our natural frequency and see what the response is. Okay, well, that's kind of our context. Now, if you have this. Now, if the omega here matches this omega, then you're going to get something like resonance. You're going to have a resistance that kind of tends to mess that up a little bit, okay? Because your R is much greater than your L, so this decreasing exponential kind of takes over. And that's a disadvantage. So I'm not sure what we're going to actually be able to observe. The problem is our coil itself, or inductor itself, has a resistance. So there's a resistance in the circuit, and I think it's a whole lot bigger than L, at least 100, maybe 1,000 times bigger, which means that whatever occurs is going to occur like on a millisecond time frame. But we can't observe that. We were able to observe stuff, just a bit of a signal that happened on a tenth of a millisecond order. Okay, so we've got the instrumentation where I think we can observe this. We want to understand this, and we want to understand this because LRC circuits are going to be. Now, if we're driving a circuit with this, no matter what our initial state of the circuit is, eventually the current function that's like an I naught cosine of omega phi. Okay. From that current function, this last time I kind of just pointed it out in the equation. Your current function is the derivative of your charge. Current's the rate at which charge is being moved from one plate of the capacitor to the other. Okay, and I think we're pretty familiar with that. Okay, so if I equals dq dt, if I is I naught cosine omega t, what's q? You take the derivative of to get I naught cosine omega t. Got to be a sine of omega t. Because to get a cosine by taking the derivative, you better start with a sine. That should be pretty obvious. So if it isn't, make sure you think about it till it is. So Q is some multiple of the sine of omega t. Now I naught is just a constant, so you're going to have an I naught in there. But the derivative of I naught sine omega t is omega I naught sine omega cosine omega t, not I naught cosine omega t. So you better have an omega here. And you can verify that the derivative of this is this. Okay. We have sine of omega t the cosine of omega t, they look like this. And I just said that. Never mind, said that. Okay. What happens to the cosine happens phase of pi over 2 later to the sine. Okay. Well, this means just a phasor diagram earlier that if the current through the resistor is like this on a circular diagram, where this is, well, where the actual current is here. Okay, so there's your actual current. Here's your phase diagram. I'll send you all about it. It tells us that Q is going to be behind pi. Okay, doing that right. Let's see. It's going to be out of phase by pi over 2. So you have it could do. That making any sense? Then try to figure out where to put this logic. Okay, so phi is this, Q is this. Then I prime, which is Q double prime, you take the derivative of this and you get negative omega I naught cosine omega t. Negative sine of omega t, well, has a graph that is the reflection of the sine, and it's 180 degrees the cosine. So negative, let's put it this way, cosine omega t times negative sine of omega t by phase difference pi over 2. That's where I've got this diagram backwards. But let's just go like this. This would be your negative omega I naught sine of omega t. Somehow I remember it being backwards, and I'll fix it if it is. But let's go with this. I'll explain a little bit more about this phase diagram, but it looks like so. Okay. Now, what we really want is the voltage. I haven't included anything to indicate the voltage except here. I take the resistance and multiply by the current, and this is a voltage. Okay. Now, what do I do to the charge to get a voltage? Well, I've got to divide it by C. Voltage across the capacitors Q over C, right? The voltage across the inductor is omega times L. Well, is the voltage across the inductor multiply the current by L. Okay. In other words, so we assume this current and we draw these conclusions. The resulting is the vector sum of these three. So I want to draw a new diagram and do just a little more explanation. Circle. Circle whatever amplitude. Where this vector has angle A, magnitude A, and angle theta, got an angular frequency omega. And this thing is going around in a circle, right? And the actual voltage might be the projection onto the x-axis. Of some theta. Make sense? That should be a familiar circular definition of the cosine. Cosine theta equals I naught cosine of omega t, right? And that's just this vector here. So this vector is going around this circle with angular frequency omega. Oh, the circles have been coming out pretty good, but I think my run just ended. So if I have y again, r I naught cosine of omega t here. Down here, I have my voltage across the capacitor, which is Q over omega c times I naught sine of omega t. This one here, as we said, is negative omega L I naught sine of omega t. Then at this point, here's the voltage due to the resistor, right? And here's the voltage due to the capacitor. It's the voltage due to the inductor. So I can call this the bar. Don't have a good place to label this. And I'll call this V sub C. Call this sub L. The net of these is this plus this negative, right? And at least with this picture, that's less than V sub R. If we take these three vectors and add them head to tail, looks like this. that what I did here? I take this vector and then I put this vector head to tail with it. And then I take this vector head to tail with that one and I get this, right? So now it's as though I have, well, this vector tells me my little voltage. Okay. And this picture shows me how it's broken down across the different components. I could have these two vectors before I do this. In the case here, I end up with just a short vector to the left, right? And I could combine that with this thing and give me the same result. Okay. That's not what I just said. These two sum up to short vector to the left, which is like right here. So it's like I can just take this vector, which is the difference of these two, and combine it with this. Okay. And this, okay, well, the thing I'm getting at is now, what am I multiplying by I naught? Multiplying the resistance, multiplying Q over omega C, or multiplying negative omega L. Um, Q there, that's one of them. Okay. This has a set, plays the same role that resistance does, and this plays the same role that resistance does. Okay. Each of these multiplies current and voltage. Okay. But you don't call this a resistance and you don't call this a resistance because this is a resistance. Or what we call inductive and capacitive reactances. Okay. They act sort of like resistance. So let's imagine that you have a capacitor and you're running an alternating current through it. A fast alternating current isn't going to have time to build up a lot of charge on the capacitor and suppress your current. Because every charge you build up in the capacitor suppresses the current that you get from your voltage. Do we understand that? That's something you've experienced. Okay. With an inductor, a high frequency is going to begin to get suppressed because the inductor fights fast changes in current, right? Back EMF. Back EMF is proportional to the rate of change of current. So if you got a quickly, a rapidly change, a frequent, a current that's changing with high frequency, just to say it precisely, then your inductor is going to suppress it. So if you got a high frequency, which one of these reactances is large and which one is small? This one large or small? Large or small? Large. High frequency, that means your angular frequency is big, high. So you got a lot of inductive reactance. So you try to run a very high frequency signal through any kind of an inductor, and you're not going to get much average current or effective average voltage then. No matter what voltage you're applying, the current that you get acts as if you applied a much lower voltage. Does that make sense? Okay. And if you got a high frequency on your capacitor, okay. If omega C is like 10 billion reciprocal ohms, okay, and then you got a very tiny number here, and practically all of the current that you would expect from your voltage passes through. Okay, now if you got these things in series, resistor, inductor, capacitor, might as well call it. Okay. Your resistor is not going to, well, not it's going to affect frequency of the current that you eventually get. Okay. Because if you keep this thing running at a constant frequency, constant amplitude voltage, okay. So you apply some voltage, 10 volts at a frequency of a kilohertz, 1,000 cycles per second, okay? Just imagine 10 volts here. If you run that through a resistor, you're going to get 10 ohms, 10 volts divided by the resistance, and that's the current you're going to get, okay? If you have a pretty big inductor here, though, that's going to fight you, and that's going to reduce the current that you get, isn't it? Okay. Or if you got a very low frequency, your capacitor is going to have plenty of time to build up a charge that negates the effect of your voltage, right? Okay. Well, that's what you kind of need to understand about an RLC circuit. The rest is just arithmetic. And the arithmetic, involves a circular model of a few vectors that are all rotating simultaneously. As one of these rotates, the other does. And what we're representing here, of course, is just, well, the current. Okay. So this whole thing is rotating with angular frequency omega. Net effect of all these three things is then clearly not a result of resistance, but it's a result of resistance and two other things, impedances. I said reactance. I don't know what's going on with my vocabulary. And now I'm confused by my vocabulary, but I'm going to go on. Yeah, those are reactances. Your impedance is a measure right? Impedance it's getting comical, but wasn't pathetic. Reactances. Let me read it again. Impedance is a measure of the net effect on your current that results from, as a result of, it's probably not the right phrase, but that results from the resistances and reactances. You got a resistance, you got a reactance, you got a reactance. These things add as vectors. Put absolute value signs around it, so I don't have to worry about whether I've got these in the right order or not. Okay. Your net reactance is magnitude of this. Okay. It's perpendicular to the resistance, the effective resistance. So impedance equals square root of your squared resistance added to your squared reactance. In symbols, we use Z for impedance. So plus square. X sub C is your capacitive impedance, and X sub L, or your capacitive reactance, and X sub L is your inductive reactance. I think your text might have those written in the opposite order. Okay, now I've straightened myself out. It is omega L minus 1 over omega C. And whatever prompted me to put a minus there was something I saw there and put down without thinking. But obviously it's a plus because you're adding the magnitude of this. Well, you're adding this, and there's your hypotenuse. It's this squared plus this squared. So that was just, I hallucinated something, wrote down a minus sign. Again, to summarize, let's think about it again. First place, the orientations of these vectors depend on the orientations of the current, okay? Or depend on the current. The phases come about because the voltage of the capacitor, well, if you take the derivative of the current on a capacitor, you get the current through, you get the current. So charge, Q is charge. I don't know, not getting the right words. Okay, again, if you have the charge on a capacitor, derivative of that charge is your current, because that's the rate at which charge is flowing from one plate of the capacitor to the other, right? And because your current is the same in the resistor, capacitor, and inductor, it follows from that, by the details we did, that the voltage on the capacitor, which we get by, well, voltage on the capacitor is going to be 90 degrees out of phase with the voltage on the resistor. And then since the current on the resistor since the inductor reacts to the rate of change of the current on the resistor, then this one is going to be 90 degrees out of phase in the opposite direction. It's the current. Okay. So that's what we did over here. Well, I can't say it right. But that's this whole derivation. And it works out. So that's correct. So I'm trying to summarize quickly and I'm messing it up. Okay. Again, think. You got the current. Okay. And it's the derivative of the charge in the capacitor, which is why this is in this relationship to this, and you just work out the details. You integrate the cosine and you get a sine with the omega in the denominator. Okay. Okay, well, I think we've established those three phases. In terms of the whole idea of what should be familiar to everybody from August and from preceding courses, the circular model, their trig functions. Okay. And again, we talk about how a capacitor suppresses slow changes by building up the charge for the anything changes, resisting or opposing the source voltage, and how an inductor suppresses fast currents. Put all that together with this idea, these ideas of inductive reactance and capacitive reactance. Okay. With this diagram, we get a pretty good idea why we're doing the square root of the sum of the squares of the total reactance and the total resistance, because it's the way this diagram is created. Okay. And again, just to be sure, this diagram here has resistance here, and it has total reactance, I'll call it X. Here. Okay. So this is the you can play around with this picture now. If you have a greater capacitive reactance and a lesser inductive reactance, then of course you have a picture that looks like this. Okay, the other thing you get here is you have a difference in phase. This angle here I don't know if you can read this, I don't know what happened in voltage. This angle here is how much your voltage, your current is out of phase with your voltage. Okay. Now, from what you know about differential equations, for everybody who's listening knows differential equations, you know that what you do with this equation, which is the source of everything I'm talking about, if you have a voltage driving this thing, okay, and you have like a V naught sine omega t or V naught cosine omega t, whatever, how do you solve the differential equation in that case? You assume a solution. You get your undetermined coefficients. And the solution you assume, well, if this is a sine on this side, whether it's a sine or cosine, it doesn't matter. You're going to have some linear combination. Q is going to be some linear combination of sines and cosines. So you just let Q equal A sine omega t plus B cosine omega t. Run it through the equation, set it equal to source voltage, and you get some combination of sine and cosine. It's going to be out of phase with the original sine. Now, is it worth doing that? We're showing you that. It's pretty simple. And you've had differential equations. If you haven't had differential equations, something you might want to ignore, but it's not hard to understand. I'm going to do this. Okay. So need much board space to do this. At least I don't think it would. Okay, if we have double prime, it's R cube prime plus Q over C equals V naught sine of omega t. You just let Q equal A cosine omega t plus B sine omega t and see what A and B have to be to make this work. All right, so well, that's pretty easy to do. Whether you know differential equations or not, you take the derivative of this, you're going to get negative omega A omega t plus omega B cosine of omega t, which incidentally is automatically 90 degrees out of phase, whether ahead or behind, figure it out. Then you got Q double prime, which is negative omega squared A sine of omega t minus omega squared B of omega t. So now your equation becomes LQ double prime. So you got I'm not gonna keep writing out the omega t. I'm just gonna use parentheses, but we know omega t goes in every set of parentheses. At negative L omega squared A omega t minus L omega squared B sine of omega t, and then plus minus R omega A sine of omega t. And all I'm doing is just put L in front of this and put R in front of this and I'm going to divide this by C in a minute. Okay. Okay, I think I've got it right. And then now I did start writing my omega t's here, just couldn't help myself. So I'll just kind of, we understand their omega t's and all these parentheses. What do you do next? Well, you sum up all the sine terms and they have to equal V naught sine of omega t. So the sine terms are this, this, and this. We conclude that L omega squared V, I think that's negative, isn't it? Yeah. Minus R omega A plus V over C equals V naught. Because these are the terms that are in front of the sine omega t on the left-hand side. V naught is a coefficient sine omega t on the right-hand side. So we've got an equation. A and B are unknowns. We're going to be able to solve for A and B, right? So we solve for A and B. Well, we need another equation, but we've got it. The sum of the coefficients of all the cosines has to be zero because we don't have a cosine of this side. Now, this should be familiar to you. If it's sunk into when you did it differential equation, I'm sure we did it. Okay. So we can simplify the equations a little bit. We have R omega A plus B over C minus L times negative L omega squared plus 1 over C equals V naught. I just took the two terms with B on them and factored out the B. So now I've got a multiple of A and a multiple of B. Here, A times negative L omega squared plus 1 over C plus V times R omega equals 0. So there's A and B. They're just got a, it's a linear equation, system of linear equations. Solve it using the determinant, okay? Anyhow, it's been a while since I had linear algebra. Think about how that would relate, okay? Now, my point is that you're gonna get A cosine omega t plus B sine omega t. Which is out of phase with V naught sine of omega t. Make sense? Now, unless A happens to be zero, okay? That's pretty much it. Now, to see how much out of phase, you got to use your sum of two angles formulas and get this as sine omega t plus B sine omega t as C cosine of omega t plus 5. We don't use C because it's your capacitance, right? So we use D. It's cosine of A plus B or alpha plus beta. Okay, go back to your Euler identity, rederive it, whatever. Haven't used it, why, I don't remember it. Just another comment. This could be written as a matrix equation. Here are your coefficients in matrix times the AB column vector equal V naught zero column vector. Invert that matrix and invert 2 by 2 matrix is really easy. And you quickly get your solution without having to do quite as much work. Okay, that's just something to remind you, because again, everybody in here's had linear algebra. If you haven't had it, have that to look forward to. Most people who take this course have had linear algebra, so are taking one. Okay. And if they're taking it, they're probably near the end of it. So that makes sense. And if it doesn't, it's not essential physics. That's kind of what you need to know about AC circuits. I'm going to have a last problem assignment, probably not a lot of problems, but things that I think might help focus everything you know.